So right now we're in the process of learning about methods for solving first-order differential equations, and we have looked at one type, and that's separable differential equations, and we looked at how you can use the method separation of variables to deal with those. So that's finished. And now we're going to look at another type, linear differential equations, and there's going to be a method for dealing with those. Now, the way I initially described what is a separable differential equation is I wrote it in a certain form. So first order differential equations all have kind of this form. By definition, a first order differential equation, they're differential equations that you can write as x prime equals and then some stuff involving x and t. Even if it's not originally written that way, you could write it that way. Separable differential equations have the more special form x prime equals some function of x only times some function of t only, so that you can then divide by the function of x only and then integrate and use the separation of variables trick. Linear differential equations, on the other hand, have the following form. X prime of t, but I'm not writing that, plus a function of t, let's call it p, times x, equals a function of t. Let's call that one q. So it's a specific form for a first order differential equation to look like, and it's not directly in this form. I mean, you have to subtract. Maybe if I did this, then you can see in what we call the normal form, it might look like that. But typically we'll rearrange it to look like this, and you'll see why. So this will be like our standard form for linear differential equations. And the method that we're going to learn about is called the method of integrating factors, which is one of my favorite methods in the theory of differential equations. It's really the first really interesting one, I think. You may have noticed that I left integrating off of this list. That was actually the first method that we learned about, but that's really a special case of separation of variables, right? When you can integrate, when you have like x prime equals and then some function of t only, then that's separation of variables where they're already separated and there's just no x's showing up. So I'm going to say integration is contained as a sub-item of the separable case. Okay, so these are called linear differential equations. And the word linear is actually something you've heard before in linear algebra, and it is that kind of notion of linear that is being referenced here. But hold off for now. I will come back at the end of the lecture and we'll discuss what exactly is linear about this. So you'll see there is something linear algebra-ish going on here. So for now, just take linear to mean can be put into this form. And at the end, we'll look at what it really is supposed to mean. Now, you could have a differential equation be linear and not necessarily immediately look like this form. You might have to put it into this form, just like when you're using separation of variables, you might have to rearrange things to separate the variables. So for example, you might have like tx prime equals sine of tx plus cosine of t. And that doesn't immediately look like x prime plus something times x plus equals something where the somethings all involve t. That does not immediately look like that. However, you could subtract the thing involving x to the left-hand side and then divide everything by t. And now you have written it in linear form. So to be even better, maybe I should write plus here and then a negative sign here. And then here is your, this function would then be called p of t. And this function would be called q of t. All right, so how do we solve these? So the cool thing about linear differential equations is that they're all solved. There's always a method for solving them, just like separable. But linear is a larger class of differential equations. So let me show you what I mean by that. You know, actually, I take back that statement. It's not that linear is a larger class, but there are some differential equations that are both separable and linear, where you could use either method, take your pick. And there are some differential equations that are separable but not linear, and some that are linear but not separable. And in both cases, separable or linear, there's a surefire way to solve your differential equation. Except the integrals might be hard. But then you can just write down definite integrals like we've discussed, and just leave some uncomputed integrals in there, which is fine. Okay, so now I want an example to show you how to do this method of integrating factors. So I'll go to the web work to pick out an example. Okay, here I found a good example. So I'm taking problem 6 from homework 2, and let me just copy that over. Okay, here it is. So I've got this initial value problem. I've got a differential equation and an initial condition. And it's actually already written in linear form for me, so that's nice. So I've got y prime plus some function of t times y equals some function of t. I actually prefer x's rather than y, so I'm going to rewrite it using x's. So x prime, so I'd like making x of t the unknown function. So x prime plus negative 3, let me keep it as minus 3, x equals 9 e to the 6t, where x is my unknown function of t, and x of 0 equals minus 2. Okay, so here comes the method of integrating factors. So, actually, before I look at that, notice that this is not separable. So you couldn't use your current methods to do it, to solve this. Right? I mean, if I wrote it as x prime equals 9e to the 6t plus 3x, can you see any way to separate this into being a function of x times a function of t? That just really doesn't look doable, right? So this is, looks like it's not separable. Now, the key for this method is multiply by a function so that the left-hand side becomes the derivative of something. Specifically, multiply the differential equation by a function so that the left-hand side becomes the derivative of a product, in the sense of the product rule for derivatives. So at first you don't know what function would achieve this, so you multiply by an unknown function. So here, let me write the of t very clearly. So usually we would just write, usually in your scratch work you might just write mu for the function, like this, and not write mu of t just out of laziness, but let me not be lazy this first time through and write things out. So I'm going to multiply by this function, mu of t. And let me write down the t dependence explicitly everywhere. So there, this is my original differential equation, but I've multiplied it by an unknown function. Okay, so why have I introduced this new additional unknown function? How can this help? What I'm going to do is search for what conditions make it so that this left side becomes a derivative that was obtained using the product rule. So here I've got mu of t times x prime of t. What I want, let me put it this way, what I want let me arrange this a little bit better. What I want is for this, to be the derivative with respect to t of mu times x. So I want to choose mu. Mu is unknown, and I want to find out what mu I should choose in order to make this left side be the derivative with respect to t of mu times x. So how do I find a good condition to put on mu to make this work? Well, I could just compute this derivative, what it would be, using the product rule. So this would be mu of t x prime of t plus mu prime of t x of t. That's what this would be, right? So then what I want is for this to match up with this. And you can see we already have this term matching up with this term. So, and we've already got an x of t here and an x of t here. So all that's left is to have mu prime of t equal negative 3 mu of t. And that would do. If I found a function mu such that mu prime equaled negative 3 mu, then I could multiply my original differential equation, I could multiply my original differential equation by that function mu, and that would do it. That would allow me to write the left side as a derivative like this. Then I can integrate and finish. So this function mu, if we can find it, is called an integrating factor. So the mu showing up here is called an integrating factor. Hence the name of the method of integrating factors. The method is find an integrating factor, which is the procedure we're carrying out now, and then multiply your differential equation by that integrating factor, and then integrate. Okay, so let's continue to find mu. So now, mu prime equals minus 3 mu. Maybe I should write the t dependence. This is a differential equation in mu, right? You could write it as d mu dt equals minus 3 mu. This is a differential equation in the unknown function mu. So let me solve this differential equation to find mu, then go back to my original differential equation and use mu to solve that. So what we get when we apply this method is a differential equation for mu. So you'll solve another little differential equation in order to solve your original big one. Okay, so how do we solve this one? It's separable, and it will always be separable every time you apply this method. This is separable, and here's how I would separate. I would say that, and then I can put some indefinite integrals down. And on the left side, it looks like I have log mu. And on the right side, I have minus 3t. And there is a plus c. But I actually don't care about the plus c in this one situation, because I am not trying to find all possible mu's. I don't need a general solution. So I'm not trying to find all possible mu's that would make mu prime equal this thing. I'm just trying to find one. If I found one, then I can apply this method. So I can choose c to be whatever makes everything the easiest, and I think c equals 0 makes everything the easiest. So here, I don't really care about the plus c. Okay, and now I can exponentiate both sides, and I've got mu of t equals e to the minus 3t. So we have found our integrating factor. Now let me go back to the original differential equation and multiply it through and see the magic happen. So I'll be right back. Let me just copy down the equation. Okay, here was our original differential equation, and now we have an integrating factor. So now I'm going to multiply through by the integrating factor, e to the minus 3t x prime t minus 3e to the minus 3t x of t equals 9e to the 6t times e to the minus 3t. And look at that. The left-hand side is now a product rule. It's the derivative of e to the minus 3t times x of t. It's the derivative with respect to t of this. And if you don't believe, pause the video and check it. But of course it should work because that's how mu was chosen. It's really quite magical that this works when you haven't seen how mu was chosen. So let me just continue writing in blue. So our new differential equation is, let me simplify the right-hand side, e to the 6t times e to the minus 3t. That's e to the 3t. And now I can integrate. So this is why mu is called an integrating factor. It's a factor that you multiply the equation by, so that now the equation becomes something you can integrate to solve. So it has enabled us to integrate. So I'll integrate both sides with respect to t. And this time I do care about the plus c because I want a general solution. Actually, if you look way back at the original problem, it had an initial condition. So I actually want a particular solution, but to get that I first need the general solution. Okay, so the left side, I'm integrating a derivative. So I just get back to the original function. And on the right side, the integral of, the 9 pops out, and the integral of e to the 3t is e to the 3t divided by 3. So I get 3e to the 3t. And now I do want the plus c. And this is a common mistake. Remember to add the plus c at the stage where you integrate. Don't wait till the very end to add the plus c. You'll see that it matters, because now to solve for x, I need to multiply by e to the 3t. And if you look at what happens now, if I multiply through by e to the 3t, I get 3e to the 6t plus c e to the 3t. And if I had not added that plus c at the right stage, I would have ended up with the wrong form for this term here. Alright, so this is my general solution. Now if I want to satisfy the initial condition, I need to remember what that was. It was x of 0 equals minus 2. So here I have x of 0 equals 3 plus c, and I want to set that equal to minus 2. So I have minus 2 equals 3 plus c, so c equals minus 5. So my final particular solution that satisfies the initial value problem is that. Let me just check. Ah, good, it worked. Okay, so that was our example. Let's now describe the general method. Say you have a linear differential equation. Remember, I've defined linear differential equation for now to just mean something you can put into this form. X prime plus some function of tx equals some function of t. Then, the method of integrating factors says to solve this, first multiply by an unknown function of t, mu, which is called our integrating factor. And honestly, this is really cluttered. I'm just going to drop the of t. And you just have to remember which parts are time dependent. Here, pretty much everything. Then look at this and decide that you want it to be ddt of mu x, and observe that ddt of mu x is mu x prime plus mu prime x, then notice that these match up. So if you want this to equal this, then this should equal this. And that is a differential equation. So mu prime equals p mu. In other words, d mu dt equals p mu. And this will always be separable. So remember here, p is a function of t. So I can leave it on the right-hand side, and I'll have d mu over mu of t equals p of t. Maybe better to just write mu there, since I'll change variables in the integration. So there it is separated, and then do an integral, and this is an integral where I don't care about the plus c. Then I get log mu, really log absolute value mu. You might have to worry about things like that, but let's not for the moment. And then integral of p of t, here dt. I'm sorry, I should have put a dt here. Here there should be a dt. And now if I don't know what p of t is, I can't like really do this integral, but I can still just leave it as an uncomputed integral for the moment, just to describe the method in general. So if log of mu is this, then exponentiating both sides, mu is e to the integral p of t dt. So there's what mu is. So that's my integrating factor. Then I can take the original differential equation, which went a little bit off screen. I can take the original differential equation and multiply by mu. Then what do I get? So let me do that. So I'm applying the same method we did on the example, and just I'm doing it in general to show you the general idea. So multiply through by this integrating factor, e to the integral p and remember this is a function of t. Then if you did this right, then this should be, the left side here should be ddt of e to the integral p of t times x of t. And then the right side is still that, e to the integral p of t q of t. Then the integrating factor has done its job, and now you can integrate. So integrate both sides now with respect to t. And at this point, if we don't know q of t or p of t, of course we cannot compute this integral, but we can leave it as an integral for now, just to show the general method. So the left side, I'm integrating this derivative, and I get back to the original function. And on the right side, I have just whatever this comes out to be if you fill in what p of t and q of t are and compute. Sometimes you cannot compute, but it becomes possible to use definite integrals to still express the answer somehow. So finally, I want just x of t, right? So here, after integrating, let's pretend that you chose a specific antiderivative here. Like when you do this integral, like when I write this integral, normally after you do it, you would add on the plus c, right? You would do this and then you would add on the plus c. Let's pretend that you chose a specific antiderivative. For example, maybe you did the integral from 0 to a particular value of t, and then you made the dummy variable here s. But I just don't want to make a choice here. So pretending that when you do this integral, you get a specific, you do it with a specific choice of c plus c in mind. Then afterwards, to get the general solution, I would want to put the plus c. So let me just put that there to represent the plus c that you would get after you did this integral. Then, when you solve, when you solve for x, you would have to multiply both sides by e to the minus integral p of t. So I would get e to the minus integral of p of t times the integral of e to the integral of p of t plus c e to the minus the integral of p of t. And there's the general solution when you use the method of integrating factors. So there are people who just write this formula down and then they say, well, just use this formula. First, write your linear differential equation in the form x prime plus p of t x equals q of t. Find out what your p and q are, and then just plug them into this formula. You can do that if you want to. Just plug things into the formula and then compute a bunch of integrals. But it's really ultra lame, I think, to do it that way. And it feels a lot more badass to just take your original differential equation, and it's not more work. In fact, it's less notation overall. To just take your original differential equation and then actually multiply by mu, get a differential equation for mu, solve that, then go back, multiply the differential equation by the mu that you got, and see the magic happen, just like in the first example I showed you here. So I recommend doing it that way, like I did that example. And take this as just a demonstration that of the method in general. If you really love formulas, go ahead and use this. But I don't think it really saves you any time. Okay, let's do one more example and try to solve this differential equation. And I'm going to use the method of integrating factors. So the method is really easy once you get used to it, and the difficulty is all going to come from just hard integrals, which I think this one has one. So here we go. First I'll multiply by mu of t. I'm not writing of t, but I know that it's a function of t. Let me write it in this order. Then I want this to be mu x prime plus mu prime x, which means I want that to be mu prime. So that means I have d mu dt equals t mu. So d mu over mu equals t dt. So that means log mu equals 1/2 t squared. So then mu is e to the 1/2 t squared. Yeah, that's it. Mu is that. So there's my integrating factor. Then I go back to the original differential equation and stick in the integrating factor. So I've got e to the 1/2 t squared x prime plus t e to the 1/2 t squared x equals e to the 1/2 t squared sine of t. And now, like magic, this left side has become a derivative of a product. E to the 1/2 t squared x. Now I can integrate. So I've got, so integrate both sides. So now the differential equation looks like this. And the right side, so I have a hard integral here. Now for a lot of the WebWork problems, since they're textbook problems, or they're problems that I chose specifically because you can do the integrals, sometimes they're hard, but you can still do them. For a lot of those, you will be able to do the integrals. But here, this is quite difficult. Now, let's say I had some initial conditions. Let's say I don't really care for computing integrals, and I just want to write down the answer in some form, and I'm okay with having uncomputed integrals in it. Let's say I had some initial conditions, like, let's say back here, in the original problem, I had not only this, but also the initial condition, maybe x of 0 equals, and let me not specify the initial condition, let me just say x of 0 equals x naught, where x naught is some number that was given to you in the problem. Then, how might I satisfy that in the way I write down the answer? So the easiest way, the most straightforward way I see to do this, there's probably other ways, is to just stick some limits on this integral here so that it becomes very clear what the value of everything will be at t equals the initial t, or whatever is the t that you're given here. So here I've put 0, x of 0 equals x naught. If I were told x of 7 equals x naught, then t equals 7 would be sort of where I have my initial information. Here t equals 0 is where I have my initial information. So for the limits on the integral here, I choose 0 to t. And now if I'm going to use t for the limit of the integral here, probably I should avoid some confusion here and use a different dummy variable for the integration. So let me just use s here. Then I can stick on my plus c, since this is now one particular antiderivative. And now I'm in a situation where I can impose the initial condition. So the initial condition was x of 0 equals x naught, right? So I can impose that at this level before or after solving for x, that doesn't matter. So let me plug in t equals 0 and x equals x naught. So if I take the original solution to the differential equation, this is a solution, just implicit because I have not yet solved for x. And then I replace the x by x naught, and I replace the t by 0. This is e to the 1/2 0 squared. Here, I get an integral 0 to 0 of a bunch of stuff, ds plus c. So I've got x naught equals 0 plus c. So in this particular example, it worked out that c is just x naught. And so finally, solving for x here, I'd have to divide by this thing on both sides of the equation. So x of t equals e to the minus 1/2 t squared times the integral 0 to t of e to the 1/2 s squared sine s ds, whatever this integral is, plus c times e to the minus 1/2 t squared. Sorry, not c. We have now solved for c. Here I've got x naught times e to the 1/2 t squared. So there's my solution. And it's a perfectly good solution even if I have not computed the integral. But of course when you type things into WebWork, you're going to want more explicit solutions, and if you can compute the integral, that is better. But this is good. This is a solution. In practice, in real life, if you can get to this stage, writing things in the form of an integral that you haven't computed, that's not necessarily bad. That's still really very good. And by the way, if you really don't like integration, which is probably true for a lot of people, you can just use Mathematica to do all of your integrals for you. So this is another advertisement that Mathematica will make your life a lot easier in this course, and probably in a lot of other courses later on. Here, let me type this integral into Mathematica and show you how that works. Alright, so I moved the blackboard here so you can see the integral right there. So integrate, and the function takes 2 arguments. If you ever don't know, you can just highlight the function or click on the function and then press F1. So when I press F1, I get this help which tells me how to use it. It gives me lots of examples, and it gives me a bunch of options and stuff like that. So anytime you don't know how to use a Mathematica command, just click on it and press F1. Okay, so here I know it takes two arguments. One is the function I'm integrating, which is going to be e to the 1/2 s squared times the sine of s. And I need to capitalize sine because that's just the name of the sine function in Mathematica. And then comma, and then the second argument for this function, integrate, is going to be the variable of integration, that's s. Then I hit integrate, and there's some answer. Now, the fact that there's these funny looking functions showing up here suggests that Mathematica's probably giving me the integral in terms of another integral. So I was not going to have much hope of just computing this by hand as some elementary looking function. I don't know what this L04P thing is, so I might highlight it and press F1. Looks like it's that, the imaginary error function. Yeah, so it's related to L04P, but there's some complex numbers stuff going on in there. Okay, so glad I didn't try to do that integral by hand. Alright, so method of integrating factors, it's really awesome.